Welcome back to Lecture 2 of Week 1 for Math 320. Before we get started, I want to remind you that there is an exercise sheet posted on D2L under Week 1 containing exercises for this set of videos. The exercises are divided by lectures, and you should try working on the exercises immediately after watching the corresponding video. Some of the exercises on the exercise sheet are already solved for you. This is to provide you with what the expected answer should look like. You may model your answers to the exercises and later to the problem sets after the shown answers on the exercise sheet. As the exercises will not be graded, you do not need to type them. However, do try to work them out on paper, as during the Monday classes, we will divide you into small groups to share your solutions to the exercises and discuss your work. It is better to have a written copy ready and not just rely on your memory of how things go. It is also perfectly okay to work with other students on the exercises, as well as post questions about exercises to Piazza before Monday. I will usually wait a few days before answering such questions so that your classmates have a chance to think about the problem themselves. Now, back to our scheduled programming. This lecture will be about the concept of countability. In the last lecture, we talked about infinite cardinality. In this lecture, we refine the notion and say that a set X is countably infinite if there exists a bijection from the natural numbers to X. A useful proposition, which is really a part of the CBS theorem from last time, is that X is countably infinite if there exists both an injection from N to X and a separate, not necessarily equal, surjection from N to X. As part of the definition, since bijections are also injections, we see automatically any countably infinite set is infinite. Countable infinity turns out to be the smallest type of infinity when it comes to cardinality of sets. We will prove in the next slide that if X is countably infinite and Y is just infinite, then there is an injective function from X to Y. Notice I am again using the step-by-step format for the proof. Step 1, there exists a bijection from N to X. This is a definition of X being countably infinite. Step 2, F is invertible. This follows from knowing that F is bijective, a fact you learned in Math 299. Step 3, there exists an injection from N to Y. This is a definition of Y being infinite. Step 4, we can build an injective function from X to Y. We will do so by letting the function be the composition G composed with F inverse. This function is correctly defined because the domain of F inverse is X and the range is N, reversing that of the function F. Hence, the range of F inverse is a subset of the domain of G, and the composition can be formed. To justify that this composed function is injective, I will defer a proof of the fact that composition of injective functions is injective to your exercise sheet. An example of a countably infinite set is Z, the set of integers. This is interesting as this means that there are as many natural numbers as there are integers. The bijection between the two sets can be given by the function f, where f of n, with n a natural number, is set equal to 0 if n equals 1, set equal to n over 2 if n is even, and equal to negative the quantity of n minus 1 over 2 if n is odd and at least 3. I leave this as an exercise on the exercise sheet to check that this function is indeed well-defined, that the range can be taken to be z, and that the function is both surjective and injective. What about the rationals? It turns out there are also as many rationals as there are natural numbers. I will give only a sketch of proof here. Since this proof does not illuminate much about real analysis, and so I will save time by omitting the details. First, by our proposition on an earlier slide, since we already know that Q is infinite, we just need to find a surjective function from n to Q. To do so, we notice that every rational number can be written in lowest terms as p divided by q, with p an integer and q a natural. We define qk to be the subset of rational numbers whose lowest term form p over q satisfies that the sum of the absolute value of p and q equals k. So we see that the rational number 0, having lowest term 0 over 1, is the unique element of q1. q2, on the other hand, has two elements corresponding to 1, written as 1 over 1, and minus 1. q3 now has four elements corresponding to plus and minus 2, and plus and minus 1 half. What we will do is list the elements of Q in order by first listing the elements in Q1, followed by those in Q2, and then Q3, and so on. Within each QK, the order doesn't particularly matter, but we can list them from the smallest to the largest to give a sense of definiteness. Since each one of QK is a finite set, eventually every rational number will appear somewhere on this list. In fact, we can roughly pin down the location by noticing that the set QK has no more than 2k minus 1 elements. And so, a rational number with absolute value of p plus q equal L will appear as one of the first L squared elements of this list. We define our function f by setting f of j to the jth entry in this list. By construction, this is a surjection. What's more important to us is that the real numbers, unlike the other three families, is not countably infinite. We divide the proof into several large steps. First, we notice that it is enough to show there is a subset S of the reals that is infinite but not countably infinite. Why? Supposing such an S exists, then first, there can be no surjective functions from n to s, for if there were, then since s is known to be infinite, there would be both an injection and a surjection, which would mean s is countable, contradicting the fact that s is known not to be countable. Second, this means that there can be no surjection from n to r. I will leave this as a consequence, in fact the contrapositive, of what you will prove on exercise 1.5 on the exercise sheet. Finally, since there can be no surjection, there can also be no bijection, so R has to be not countable. We use a set S instead of all of R for technical convenience, as you will see in a minute. We take S to be the set of all real numbers that is strictly bigger than 0 and strictly less than 1, and such that the digit 9 does not appear in its decimal expansion. The restriction about the digit 9 is to avoid a well-known problem in decimal expansions. For example, 0.2399999 and so on is the same number as 0.24. So there is some degree of ambiguity. By avoiding the digit 9, we avoid this possibility. Of course, I am assuming you have some prior knowledge about real numbers here, specifically that they have decimal expansions. Notice that every element of S has a decimal expansion with a 0 before the decimal point. Here's the meat of the proof. We will show that there is no bijection from naturals to S. We will argue by contradiction. Suppose that F is a bijection. We will write out the decimal expansion of each of the numbers f of 1, f of 2, and so on. And we will use another diagonal argument to build a new number sigma. we set it to have a 0 in front of the decimal point. For the first digit after the decimal point, we choose among the digits 1 through 8 one that is different from the first digit of f of 1. For the second digit, we choose among 1 through 8 a digit that is different from the second digit of f of 2. More generally, for the nth digit, we choose among 1 through 8 a digit that is different from the nth digit after the decimal point of f of n. This builds the decimal expansion of sigma. Now sigma is in S, since firstly, it is a real number. Secondly, since it has a 0 before the decimal point, and every digit after is between 1 and 8, we know that sigma is between 0.1 and 0.9, and so is strictly between 0 and 1. Finally, sigma has no digit equal 9. However, sigma cannot be equal to f of m for any m, because it would differ from f of m at the mth digit. This shows that there must be a number sigma, which is not among those listed by the function f, and so f cannot be surjective to S, proving our claim. To bring a bit of summary to this part of the warm-up, we are interested in counting, specifically how many elements there are in a set. We see here a first significant difference between the reals and the other numbers, including the rationals. Namely, there just seem to be a lot more of the reals. We will explore more differences in the coming lectures. That's it for today. See you next time.